Yeah, okay. So
Okay.
if you're ready, just maybe do some introduction. So welcome everyone to the first afternoon session. The first talk will be given by Paul Bastide. He's a postdoc at the University of Oxford, and he's going to be presenting us a very nice short paper that I think is great, improves on a lot of problems, and he will be talking to us about, and it's about exploring temporal graphs. Paul, you can go ahead.
Thank you. Thank you for the lovely introduction and the occasion to talk about my work a bit at this workshop. Thanks a lot for the organizer too. So indeed, I'll talk about what I also think, maybe I'm biased, but that's a very cute paper. It's indeed, I think the first version was something like 4-page with 2-page of introduction and references. So you can do the math, but that's not a lot of proof, but it's still, I think, very cute, introduce some new ideas and new things that could be useful for exploring temporal graph. My co-author on this work are Carla Grunland, who is in Delft in the Netherlands, Lucas Mitchell, who was a PhD in University of Oxford, just graduated and is now moving to Zurich to work with Benny Slukov, I think. And Clément Rambaud, who is also a PhD that graduated now. He was based in University Côte d'Azur and is now in the process of moving probably to Darmstadt to work with Michał Pilipczuk. Okay, so let's talk a bit. Oh yeah, I should mention that I cannot see the chat. So if you have a question, please feel free to interrupt me at any time and just ask me the question during the talk. It's completely fine. Okay, so let's introduce things. Probably for the 5th time or more today, I'm going to talk about temporal graph. So I won't go into too much detail about what they are. I guess you all know, but maybe I'll just say that I see that as a sequence of graph indexed by some time interval. And I really take the snapshot vision. I think it's the most suited for this specific problem. So a snapshot is just one graph at some times t. And then the union of all those snapshots is what I call the underlying graph. Okay, so it's a sequence of graph on the same vertex set. Right, and I will be interested in reachability question. So I need to define what I mean by walk. There's multiple definitions you could take. What I will take today, what we'll take today is the following. If you are at some vertex v at some point, then what you can do at time step I is either you stay at the same vertex or you use one edge and only one at most in the graph gi, so exactly at the snapshot at times I. So the length of a walk is the number of snapshots you need to take in order to go from the start of the work to the end of the walk. In particular, even if you use only one edge during the whole walk, but you take edges to do so, the walk will be very long. So it's really about the time you take and not really about the distance you travel. That's what I call walk, and that's what I call the length of a walk. And now we are interested with a problem that's very similar to the travel salesman problem in static graph, which is the problem of exploring your graph G. So I want to find a walk that is visiting every vertex of my temporal graph in the least amount of time. So usually the question is trying to minimize the length of such an exploration. Right. Good. So if I just stop here and try to get any bound on the length of an exploration in over every possible temporal graph, I really easily find some kind of blockage, which is just what if the graph is not connected? So it could be that my graph is just always empty for all time step, and then my exploration is infinite. Or even though there is just 2 connected islands temporally, but the rest is not connected. So yeah, so I need some kind of connected assumption, which is normal. It's also something you need if you try to do travel salesman on a static graph. Right. So the connected assumption that I will take is just the always connected. So for each snapshot, the graph on this snapshot is connected. And this is already enough to get a finite bound instead of an infinite bound. So you can get n squared bound. And this is something that was known. And the proof of this n squared bound is quite interesting. It goes through this lemma that sometimes refers to the reachability lemma that goes as follows. For any 2 vertices uv in my graph, there is always a walk of size of length n-1 from u to v. So basically, I'm always connected in n-1 time step if I am always connected temporal graph. And to see that is quite easy, but it uses interesting fact about why is it that it makes it easier to connect things when you're always connected. And the principal idea is the following. If you define this FUT, which is what I call the forward ball at U at time step t, which just mean all the vertices that you can reach by this walk, starting from U at time 0 and then stopping at times t. Okay? So this is some kind of set. And what you can see is that, of course, FU of 0 is just U. You can start at U and not move, and you're still at U. And what's interesting is that if you're always connected, either FUT contains already the whole graph, and you will be happy for the lemma, or there is some vertex that are outside FUT, but because the graph is connected, there is no zero weight cut. There is no cut where there is no edge at all. So in particular, they need to be an edge going from the outside of FUT to the inside of FUT, or the opposite. Okay? And in particular, the other end of this edge will be in FUT plus 1. So what it means is just that these FUT sets, they are strictly increasing. Okay? They start by containing U, and then they are strictly increasing until they contain everything. So in n-1 step, at most, if they just grow by 1 at each steps, they will contain everything. Okay, I hope this is clear. Now what you do is just you fix an arbitrary order on your vertices, and you say, well, I will go from, let's say, U1, U2 up to UN, and I will go from U1 to U2. It takes at most n-1 time steps. Then I go from U2 to U3 in n-1 time step again, and this sum up indeed to n squared. Right. So this is the first thing you can remark. And then the natural question that comes is it optimal? Does there exist some kind of always connected temporal graph that achieve this n squared bound? Because in the static case, if you want to just visit all your vertices and you have no weight on your edges, you expect that to be able to do it in linear time and not n squared. And indeed, there is something different from the static case and the temporal case. And there is a case in which you need this n squared. So let me try to describe the graph for you. So you split your vertex set into two sets of size n/2. So there's the top set here and the bottom set. And you put centers of stars. You put stars that are always centers at the top vertex. Okay. So for example, at T1, you center it at the first top vertex, then T2 at the second, then the third, and you continue like this. It will be the fourth, the fifth, and then at time step 6, for example, it will come back to be the first vertex, the center of the star. So for now, I'm just describing a temporal graph. So it's a temporal graph. I define for each time step modulo 5 here. I will have a value. Right. And now let's talk about exploration of the graph. So actually, exploring the top vertices is not hard. What will be complicated is going from one bottom vertex to another. And if you try to do so, I guess the main thing to get the intuition of how it works is just try. So they are all symmetric. So let's say you start in the bottom left here, and you're trying to go to the next one. Okay. Then I claim that you need n/2 steps in order to do that. Why is that? Well, at some point you will need to go back to the top because the bottom set is always an independent set. So you somehow need to go back to the top in order to be able to reach the bottom again. So, well, it's all symmetric, right? So you can suppose that you just go back to the top at the first step. But now what happens is you use your edge at time step 1, for example, and you get to this orange vertex. Then at the next time step, the centers have moved. And now your only choice is either to stay at the same place you are or to go to the new center. But if you go to the new center, the center moves again. You're always like running after the center, and the center is always one step ahead of you. So actually running after the center is never gonna get you anywhere if you want to go back down. So the best strategy is just to go to the center at the first step and then to wait the n/2 steps until the center come back to be the same center, and now you go down and you visit a new bottom vertex. I hope this is clear. Anyway, the whole conclusion of this is that to go from one bottom to the other, you need n/2 steps, and there is n/2 bottom vertices, which means that this graph, there is no exploration in less than n²4 steps. Okay. Now that you have this, you have both your upper bound and your lower bound, and they are matching, so you're quite happy, but you would like to say a bit more about this exploration. And the next thing natural is well, probably we can put some condition on the graph such that maybe we can break this n squared upper bound, okay, and improve the time of the worst case for the exploration. And there is multiple reasons you could think so, is that the example that I just showed you, it's very specific in some sense. First of all, at each time step, it has very high degree vertices, the center of the stars. And if I look at the underlying graph, which is the union of the stars, this is actually a click on n/2 vertices and a complete bipartite graph on n/2 vertices. So this is a super dense graph. So maybe you can think that if I restrict one of the two, or maybe the two, I can improve this n squared bound. And people have looked into it. So the first sequence of paper was first from Erlebach, Hoffman, Kammer, that was then improved by Adamson, Gusev, Malicious, and Victor Zamarev, who proved that if you indeed restrict the underlying graph, in the case of planar graph, then you can beat this n square bound by a polynomial factor. And it starts by n to the 9/5 and then got improved to n to the 7/4. And they also did the same kind of analysis for tree-width scale when the underlying graph has bounded tree-widths. And it was first proved something of the order n to the 3/2, where the dependence on the tree-widths was super linear, which was then improved to be linear. Okay, so those things has been studied, and it seems that it's quite optimistic. We can indeed do better than the n squared bound if we restrict the underlying graph. Okay, and there has been way more than just those two cases that have been studied. For example, if the underlying graph is a cactus, a 2x(n) grid, or a path, all those cases have been studied. In those cases, the question is often more about the log factors, like is it linear, is it n log n, is it n log to the 3n, etc. But even those questions are quite hard, actually, and for some of them still open. So actually, even for simple graph, or a simple graph at each time step, simple underlying graph, this question of exploration are quite hard, which is not super surprising in some sense, because, I mean, the question of exploration, even in static graph, is quite hard. Right, okay. So the other side would be, let's forget about trying to put constraint on the underlying graph and try to put constraint on the snapshot. Each snapshot has some constraint. So maybe what you could do, one very natural thing to do is, let's put bounded degree on the snapshot. So each snapshot has bounded maximum degree. Then in 2018, Erlebach and Spooner also proved a sub-quadratic bound by improving it by roughly a factor of log n. So showing that this worst example of the star is not going to be matched in this case. And it was then improved 1 year later by Erlebach, Kammer, Luo, Sajenko, and Spooner to a polynomial factor lower than n squared, n to the 7/4. Okay? In the direction of lower bound, we have two cases, actually. There is one of those cases that I was talking just before about paths that are a bit complicated. Actually, you can design temporal graph where all your snapshots have paths, but still the exploration takes n log n. So this log factor is needed somehow, even though path has maximum degree 2, right? On the other side, if you look very closely at the star example that I showed you just before, that achieves n squared in general, if you restrict the star to have bounded degree d and you make multiple stars in a row, then you'll very easily convince yourself that actually this gives you a bound of d times n, if d is your degree. Okay, so we have this n log n on one side and dn on the other side, and it's still quite below this n to the 7/4, which is the best upper bound we knew. Okay. What we did with Carla, Lucas, and Clément is improve this. We really looked at this bounded degree snapshot at first, and we managed to improve the polynomial to n to the 3/2 times some function of d and log n. Interestingly, we get the square root d here, which means that somehow if you want to go, let's forget about the log for now. If you want to go to the optimal lower bound to our bound, it's a bit like trading n to the 1/2 factor with a d to the 1/2 factor, the thing that you need to do. So this is how far our bound is from being optimal, which is still quite some work to do. And then what happened is when we finished the proof, it was a very small proof. I will try to talk about the proof a bit. It's still quite intricate and quite delicate. So I encourage people that are interested in reading the paper. I won't have time to give all the details here, even though it's quite short. But we realized that our proof is actually very robust in some sense. And it has not so much to do with bounded degree of every snapshot. It more has to do with some kind of average notion that I don't think was defined before, but please tell me if I'm wrong, which we call the average temporal maximum degree. So maybe that's a very long name. What it means is that you take the average over all vertices of the maximum over all snapshot of your degree at vertex U. Okay? If you don't really grasp what this parameter looks like, the only conclusion, I want you to make two conclusions from this parameter. First of all, it's indeed bounded if each snapshot has bounded degree, because this max inside the sum is bounded, because for each snapshot I have bounded degree, so the max over all snapshots is also bounded. And then I just take an average. So I'm always happy. If snapshot have bounded degree, then I'm happy. Okay. But it also bounded when the underlying graph has bounded average degree. And that comes from the fact that the worst case I can do for this specific parameter is just to take all my edges. This is going to blow up my degree as much as possible. And if I take all my edges, this thing sum up to the average degree of my underlying graph. Okay. And in particular, the planar case and the tree width k case that was studied before are two classes of graph that we know have bounded degree. For those that are a bit more familiar with structural graph theory, this comes from the fact that those class of graph are actually defined by minus freeness. Okay, and so our proof extends to this more general class of just KT minor free graph, underlying graph. Okay, for which nothing was known about exploration, but just using our proof and the fact that it works for average degree and not just maximum degree tells you that you have a sub-quadratic exploration for those quite general classes of graph. Okay. Right, so I have a tiny bit of time to tell you something about how you prove this. If there is one thing that I would like you to understand about this proof is that I think the beautiful thing in the proof is this lemma. It's not the proof in itself, but it's this specific lemma, which is saying something that looks very naive in some sense, but that's actually the core of the proof. It just says that for any set of vertices S in my graph, so you have to think of this S as the vertices that are not yet visited, okay, and you want to visit in the future. Then there is two of those vertices that are not yet visited, U and V, such that there is a path of length roughly n divided by S, and there is an error factor, which is 2 times the degree. Okay, so for now, I'll just talk about the max degree, and you should think about this max degree. You should forget about this more general notion. I think it's only interesting if you look more deeply into the paper. For the idea of the proof, it's completely fine to just think about the max degree of the snapshot. Okay. So this thing could look quite naive, and it's very true in static graph. If I have a static graph, actually, this thing is true without any delta correction factor. Yeah, for example, I take this thing, and I want to prove that if I take 3 vertices in my graph, then there is 2 of them that are at distance at most 2n over 3. Okay, how you do that? Basically, you grow balls around your vertices of neighborhood. So the first neighborhood, it contains the vertex set itself, and then because the graph is connected, your neighborhood are growing by 1 at least at each steps, and at some point they need to intersect. And as soon as they intersect, for example, if they intersect after the kth neighborhood, then the distance between any 2 vertices would be at most 2k. You go to the intersection point, and then you go to the new vertex. So those things are growing at each time step strictly, a bit like the forward ball before, but now we also have the property in static graph that if they intersect, then it means the existence of a path, okay, which is not true in temporal graph. Okay, it's not because you can reach the same vertex at timestamp t that there is a walk from one to the other, to one point to the other. Okay, that's more complicated than that. But the intuition is that somehow, if you are bounded degree, then it behaves the same as a static graph on this aspect. Okay, so this is what I draw here. For example, this is a very simple graph, and it's true that both can reach the middle vertices in one step, but they can still not reach each other afterwards, right? In a temporal sense. Okay. But one thing is true, though. One thing is true is that if you have a loop, so what I call a loop is this, so if you look at the drawing on the right, this left vertex, it can reach the middle vertex in t steps, and then from t to L, it can also come back to the left vertex. Okay, so I say that the middle vertex is on a loop from the left vertex. Okay, and this is true now that two loops in a temporal graph cannot intersect without having a path from one endpoint to the other. So here it's the case. We have two loops that intersect on this middle vertex, and whatever is the value of t and t prime, so you can suppose maybe that t is less than t prime, what you can do is go from the left to the center from 1 up to t, then go from the center to the other side from t prime up to L, and size t prime is less than t. This is indeed a correct path. Okay, so that tells you that the set of loops has this nice property that they cannot intersect without getting a path, which is exactly what we would like. Okay, but it happens that sadly, if you just consider that, you cannot easily prove that the set of loops is increasing, so that at each time steps there is another vertex that is on the loop from you, for example. Okay, so you need to do something a bit more complicated. I won't go too deep into the proof. I just want to show you maybe the vertex that is this witness of the loop, quote unquote loop. So it's not exactly a loop. We'll take something that is slightly different than a loop, but that just end up working out for a proof. So we have still these forward balls at AT, the FAT, and we have also the backward balls, AT. So this is the thing that are the other side of the loop. So the backward balls at A at times t, it's all the vertices that starting at time t and stopping at time L can come back to A, okay? And so this is two sets. So they have an intersection. The intersection is not empty. A is in the intersection of the two, okay, at any time steps. And because my graph is connected, first of all, it's also satisfied the fact that I cannot have another of those vertices in S that are inside this set, otherwise there is a path. There is a path from anyone from A and this thing, because in particular it's contained in this forward balls at times t minus 1, okay? So they cannot intersect. Now, are they growing? Well, not exactly, but still, there is one thing that is interesting, is that the graph needs to be connected at time step t, so there is this edge going out, and this vertex, that is the other side of the edge, is the important witness, is the set of vertices that I want to make growing at each time steps. So it's indeed growing because those things are well defined. There is always such an edge, so I can always define such a WAT, okay? And now it's a bit more messy than in a static graph. It could be that sometimes they are equal. Well, if it's not the same vertex that you're recording for, and it's not the same time step, there is a path. You can convince you maybe by this drawing. But if it is the same vertex, then it can be recorded actually multiple times, but never more than 2 times actually. If it is recorded 3 times, there will be a problem. I won't go too much into details. And if it is at the same time step, this is where the degree condition came from. If it is at the same time step, then it needs to use a different edge to go to these WAT vertices at the same time step, okay? But this middle vertices here in pink, it has bounded degree, okay? So there is not that many vertices that can record it at the same time step. Because if they were recording it using the same edge, then actually there would be a path. Okay, the goal was not that you understand completely the proof of this. I did it in 3 minutes. You should read the paper if you want to understand it better. I just wanted to understand what kind of object we are using in this proof. Okay, and so this gives us this lemma. Yeah, and maybe I should just stop here. This is just a summary of our lemma and then the result we can deduce from that. And I will stop here. Thank you.
Thank you very much. Thank you very much. Sorry. Thank you very much for the talk, Paul. Are there any questions? Either here. Okay, we have a question here from the audience. Give me a second.
Thanks for your nice talk. And I just noted that you mentioned there is some more result in the restricted cases when you introduce the background. So I was wondering, and you also use the path, take path as the example when you explain the core lemma like this. And so I was just wondering, is there like better bound for these very restricted cases, say passes? So is the bound tight or?
That's a good question. So what we have is what I give a glimpse here. So the bounds is tight in general. So we can construct a temporal graph for which the bound is achieved up to a factor 2, I think even. But it looks like this. It doesn't have to look like this grid, actually. I think you can kind of make it like a path with a bunch of vertices hanging out of it. It does need to have quite a few vertices with degree d, which is your degree, your maximum degree. And basically, the only thing that are important is that the set of centers. Oh, okay, so maybe I should describe the graph a bit better. It's this grid, and then the set of centers is a column of this grid. So it's moving, for example, at times t is this one, and then at time step t+1 it will be this one. What is important is not really the structure of the black graph. It's actually just the fact that the set of center at times t are all at distance at least 1 from the set of centers at t1, and etc. This is like between time step t and time t plus I, you want all your center to be at distance at least I, which simulate these things that you cannot run after you center because they are always getting away by one more step each time. That said, we didn't think so much into can we get better bound for this in specific underlying graph or specific snapshot graph, which could be very interesting, yeah.
Okay, thank you.
Do we have other questions?
I have a question.
Thomas, you want to go ahead and ask?
Okay, yeah. So first, I just want to say this is a very nice result.
Thank you.
And so I'm just curious on your opinion. So now you have this improved upper bound of n to the 1.5 for constant degree snapshots, and the known lower bound is n log n. So based on your feeling or intuition, where do you think is the true worst case? Is it closer to n to the 1.5 or closer to n log n?
Yeah, that's a very good question. I would like to say that I think our bound is tight, but I don't think it's the case. I think it's closer to the linear case. It's mainly, if I have to give a reason why I have this intuition, it's very based on intuition, of course. It's just that the second part of our proof. So once we have this nice lemma, we use it to try to define paths that are very short and visit a few of the vertices that are left to visit. Okay, and the way we do that, it seems that, this is definitely where we lose this factor square root n, and it doesn't seem to be completely necessary somehow. It just seems that it's very hard if you want to track things more properly over the whole exploration. We are somehow, because we want to make the proof work, we are somehow forced to look into a very specific set of time step, and we do not use the fact that everything is correlated and you could do something else in order to be better in the future. So there is still some kind of leeway. To be fair, I'm not even completely convinced that using this nice lemma that I talked about in talk, we could not be more clever than what we did in order to get n3/2 or to get a better bound. It's just the best that we could do with it, but yeah, I'm not convinced. It's the best overall. Thank you.
Okay, we have time for one last question. Okay, so let me ask something. If you're aware, Paul, so there was also a few results on exploration of random graphs, and there was, if not results, at least some open question as far as I remember of having bounded degree. Are you familiar with those results, or whether your technique can be used to improve there?
Yes, this is actually reading this paper about random graph that we started knowing about this problem and getting interested into it. So we looked into it, and we actually have a positive result, which is not out yet, but should be out very soon, which goes as follow. If you have, so for those that don't know about this random setting, what you have is you sample according to some fixed distribution all your snapshots one by one. So they are independent samples according to some distribution. If you restrict the degree of the graph you sample, then now you are linear, and we can prove delta n and some polylog. And the right conjecture would be that it should be even square root of delta times n, times maybe some polylog. We don't have the square root yet, but we'll already have linear. And this is using our lemma and some other actually quite cute tools. And this is also not going to be a very long paper. So I'm quite looking forward to putting it soon, probably available.